Hello, my name is Mark Plechnik and I'm a postdoc working in the Biomimetic Mill Systems Lab at UC Berkeley under Director Ronald Fearing. This presentation is on the computational design of robot locomotion through large-scale route finding under NSF grant number CMMI 1636302. We are motivated to create design tools that advance the locomotion capabilities of small, inexpensive robots by computing new, unintuitive mechanisms. Many small robots able to negotiate rugged terrain would be useful for locating survivors in an earthquake disaster zone. An example robot with novel locomotion capabilities is our newly designed Salto robot. Salto is able to perform high-amplitude, high-frequency jumps by implementing a strategy termed power modulation, which has been observed in bush babies and bullfrogs. Power modulation is implemented automatically by the leg linkage during the sub-200 millisecond time span of ground contact. The linkage has a tuned variable mechanical advantage throughout its stroke that allows a series elastic actuator to transiently store some spring energy during stance. As the leg extends, the return of this spring energy delivers a jump 3.6 times more powerful than the motor's limit. Simultaneously, the leg linkage balances angular momentum and minimizes impulse loading during its motion. In order for Salto to perform as desired, we map its functions to a set of required behaviors. Abstractly, Salto can be broken down to a motor and gear train, a leg linkage, and a foot. We want to design the unknown leg linkage so that the robot exhibits the required behaviors, namely, that the foot traces a straight line, that it has a long stroke, that its line of action passes through its center of mass, that the linkage dimensions are compact, that the input link rotates over a large range, that mechanical advantage is low at the top of stroke, that a near constant ground reaction force is exerted for the rest of stroke, and that angular momentum is balanced. Starting from scratch, we don't have a clue what this mechanism might look like. Once we have defined our requirements, our approach leads to an exploration of the design space that generates an atlas of candidate designs that satisfy the primary requirements. Here we show a sample of an atlas of multi-loop linkages that trace a long straight line, with input pivots near the line of action in relatively compact dimensions, satisfying many but not all of the requirements. The rest of the requirements are satisfied by selecting a design to kinematically tune by performing iterative optimization, resulting in a final design. The key stage of our approach and the focus of our work is the design exploration phase. Since this phase does not begin with pre-existing designs, it is not amenable to optimization techniques that require starting points. Furthermore, by leaving design parameters unspecified, we are challenged by the curse of dimensionality. The approach we take to design exploration reformulates this phase into finding routes of massive polynomial systems. In order to generate an atlas of design candidates, we first encode motion requirements into polynomial systems of which the solutions to those systems describe candidate designs. For example, requirements on positions and velocities would be encoded into polynomials. The challenge then becomes finding the routes to the resulting polynomial system. Finding the roots to these polynomial systems is difficult because they are a very high degree. The state-of-the-art technique for their solution is called multihomogeneous homotopy. However, applying multihomogeneous homotopy to a benchmark 4-bar problem reveals that 97% of computational effort is dedicated to finding so-called infinite roots, which have no engineering relevance. We propose the finite root generation method, which entirely eliminates computations to infinite roots. The method functions to find all routes to a target system by generating a random mechanism from which a homotopy start system can be constructed, and randomly selecting configurations of this mechanism to construct a finite root of that start system. This start point could be tracked via a parameter homotopy to a route to the target system. The advantage of the method is that the route is ensured to be finite. The algorithm continues to iterate in this manner with the disadvantage that a route may repeat because of the random process introduced. We have shown that the duplication rate can be modeled as blindly picking coupons from a box. That is, say there are 6 different colored coupons in a box, and we have the goal of picking all 6 at least once. For our first pick, the probability of picking a new color is 100%. For our second pick, the probability decreases to 83%. For our third pick, the probability is 66%. Eventually, we will start picking repeats. However, the expected number of picks can be calculated. Applying FRG to the benchmark problem follows the probabilistic expectations well, and it is found that FRG requires less computational effort than current methods. We hope by reducing the computational requirement that FRG unlocks the doors to computing larger problems in limbed robot locomotion. Thank you for listening to our presentation.